So thank you very much for the very kind invitation. I'm happy to be here. I'd like to visit Erlangen sometime, but we'll see. So today I want to talk a little bit about a new optimal transport model that I came up with. And so I'll try to start slowly, even though we had a nice talk by Jan 2 weeks ago, I think now, about this. But I'll still try to cover the basics in optimal transports. And but first of all, let me start with some motivation, because I didn't come up with this model just out of nowhere. I had motivations, very specific ideas. So it has been known, at least in the optimal transport business for now 20 years, that if you use some advanced optimal transport geometry, let me put it like that, the usual linear Fokker-Planck equation, which is ubiquitous in physics, biology, and whatnot, can be considered as a variational gradient flow equation in the space of probability measures. So instead of considering it as a classical PDE, you view it as a dynamical time evolution of probability measures. And this has a nice variational gradient flow structure. This is for continuous optimal transport, and there has been recently a very nice advance in this direction, which gave a discrete counterpart to this setting, and this is due to Jan Maas. Which covers essentially the case of optimal transport over discrete spaces, so discrete graphs, if you like, and the resulting evolution equations are not PDEs anymore, but they're rather irreducible, reversible Markov processes. Recently, I got interested in a very specific Markov process, which is the so-called Moran process. So this is a model from population genetics, if you like. So you have a population of constant size, say n individuals, and each of them can have either one of two genes, so type A or B. So here these are the blue genes or yellow genes. And the variable you might want to use to describe the composition of the system at type T is, say, let me call I the number of blue genes, because just because the population is fixed, if you know that there's I blue genes, then automatically that means that there's n minus I yellow genes. And the process goes as follows. So at each iteration, what you do is you pick one individual at random, so with a uniform distribution, and you kill it. So this is this barred blue guy, so you kill it. And then you replace it. So you you're gonna enforce some kind of reproduction law, but the way you select an individual type A or type B to be reproduced depends actually on the current composition of the system. And more precisely, you sample for reproduction according to a binomial distribution whose parameter P is given by the current composition of the system. So here there's 1, 2, 3, 4, I think there's 10 individuals. At the current state, there's apparently 8 blue and 2 yellows, which means that if you kill this blue guy here, you're going to replace it by some type A or B, and you have 80% of chance to replace it by a blue type and 20% to replace by a yellow type, okay? And then you iterate this process generation after generation. This is a well-known model in evolution genetics. What happens is that, at least formally, but also rigorously, you can prove this, that in the hydrodynamics limits, when you send the size of the population to infinity, what you need to use now to describe the state of the system is not just a discrete variable I taking values in between 0 and n individuals, but the continuous fraction little x that varies continuously in between 0 and 1. So if you'd like, x represents the percentage of the population, of the continuous population with type A gene. And the corresponding Markov process that corresponds to the discrete Markov chain is now this stochastic ODE, SDE, stochastic differential equation. So dxt equals square root x 1 minus x times the standard Brownian motion. And at the PD level, it's some type of Fokker-Planck equation, which is dt rho equals Laplacian of, huge parenthesis, x times 1 minus x times rho. And what you might observe at this stage is that there are actually very delicate issues which are absorbing states. At the discrete level, this is very easy to see, because by definition of my model, if for some reason at generation k, I only have blue genes, then the only thing I can do is kill any of the individuals, fine, but then the only thing I can do to replace it with is sample among 100% of blue genes. So I can only replace it by a blue gene. So if for some random reason you end up with a population of only blue genes, you will remain so forever afterwards. And same, of course, for yellow genes. So these two states, only blue or only yellow, are absorbing states. And in the SDE here is the same phenomenon, meaning that if here X wanders off randomly at 0 or 1, then the volatility is killed. Square root of X, 1 minus X, vanishes at 0 and 1. And therefore, the Brownian motion gets stuck there forever afterwards. And this actually prevents from applying the usual standard theory in optimal transport. So what this means is that you need for an adapted geometry that would take into account such interaction between, so the bulk, if you think of the continuous world here, X varies continuously in 0, 1. So 0, 1 open interval is the bulk, the interior of my spatial domain. And the interface or the boundary is just 0 and 1 separately. So I need to come up with some kind of clever geometry that takes into account this kind of interactions between the two worlds somehow. So let me just maybe now cover the basics. What is optimal transport really? So you can think of it like this. So you have here a pile of sand, X, and you're asked to transport it to a target destination, which is another pile of sand, Y. And you want to do this in the cheapest possible way. So the way to model that is a pile of sand is going to be described by here a probability distribution, mu of X. And here the target's distribution is another probability distribution, nu of Y. So both have to be need to have the same mass. You transport 1 kilogram of sand towards another kilogram of sand. And the optimality criterion is as follows. So you decide for some reason that the costs per unit of mass to take 1 unit of mass at X and transport it towards 1 unit of mass at Y is the square distance between Y and X. There are other choice for the cost functions if you like, but let me focus on the square distance here. So the original definition of the Wasserstein distance here in its so-called Cantor-Robbich formulation is as follows. So you define the squared Wasserstein distance between your probability measures mu and nu as the optimal value of an infimization problem, where what you minimize is among all possible transference plans. So these guys pi or measures on the product space. And you can think essentially as d pi of x, y as the infinitesimal amounts that you will actually transport from location x to location y. It is actually very possible that one point x is split towards two targets, y1 and y2, say. Okay, so this allows for a very flexible setup, if you like. And then once you have an admissible coupling pi, you integrate the infinitesimal cost, which is here the square distance, and then you integrate over the product space. The only constraint that you have is that pi, the transference plans, should match the constraints you have, which is that you should actually transport mu towards nu. So mathematically, it means that for those of you who know what marginals are, it means that the first marginal of nu on the x factor must coincide with mu, and the second marginal of pi on the y factor should match nu. So this is this is a classical formulation of optimal transport, but it's a completely static formulation, meaning that the only thing that really matters is which points x is sent to which point y, and you don't know what happens in between. So there has been recently, just one fair warning, because I'm also PDE by training. In this whole talk, I will work on a space X, which is a bounded smooth domain in RD, omega. But for me, omega is compact. So if you like, compared to usual PD notations, my omega is your omega bar, right? Just for a notational convenience in some sense. So really keep in mind, and I'll come back to this later, that omega is closed. Omega actually has a boundary included in it. So as I was saying, there's a very nice dynamical reformulation of optimal transport, which is the so-called Benamou-Brenier formula or theorem, which is also coincidentally 20 years old about now, which is as follows. So if you want to compute here the squared distance, the squared Wasserstein distance between two measures ρ0 and ρ1, there's actually a very nice way to dynamically transport a measure ρ0 to ρ1, which is here solving continuity equations. So V is a velocity field that you will use as a control parameter to drive ρ from ρ0 to ρ1. And as soon as you do that, there is a very natural quantity to compute, which is kinetic energy. So if you think of ρ as a mass, by the way, in terms of notations, whenever I write ρ sub t, it's not a time derivative. It's just to emphasize that everything now depends on time. Okay, so sub t does not mean derivative with respect to time. So whenever you compute, whenever you pick a vector field V solving the continuity equation, there is a natural quantity to compute, which is the kinetic energy. So if you think here of rho t of x as a mass, this is squared velocity times mass with the correct 1/2 factor. So this is, of course, kinetic energy. And then you integrate over the whole domain and over the whole set of times between 0 and 1. And the theorem is that if you infimize this global average kinetic energy among all possible solutions of the continuity equation that match your boundary conditions, which is ρ0 at time 0, ρ1 at time 1, then you do retrieve the previous Wasserstein distance, or actually the squared Wasserstein distance. So you see here that this is a dynamical formulation of optimal transport. In particular, it allows a very nice interpolation, if you'd like. So this is a classical example that I stole from Gabriel Perret. This is called from a cow to a duck to a tortoise, right? So you model, if you'd like, shapes by mass distributions, probability measures, and then you do this kind of a dynamical interpolation between the shapes. So this is what it allows you to do. And there's a fundamental example that I want to cover is the case of Dirac delta measures. So here, if you take ρ0 and ρ1, two Dirac deltas located at two different positions, x0 and x1, then the unique solution of the optimal transport is, well, there's a natural thing to look, is oh God, I should erase this. Yes. The geodesic between the particles x0 and x1. So this is just the linear usual interpolation, the straight line between x0 and x1. And then the solution of the optimal transport is given by the traveling Dirac located at time t at precisely xt. So you see here, you have ρ0, which is a Dirac mass at 0, ρ1, which is a Dirac mass at x1, and the solution at time t is just a Dirac mass located at the solution of the geodesic. So you might notice that by very construction, this is mass conservative. The fact that I put here 0 on the right-hand side in the continuity equation, and I should have mentioned this earlier, no flux boundary condition on the boundary of your domain, means that rho t will remain a probability measure for all t. So mass is preserved. And as you can guess from this picture, this is based on horizontal displacements. Now, there's another type of distance between the probability measures, which is called the Fischerial distance. And the Fischerial distance is defined as follows. So if you take now two positive measures, ρ0, ρ1, that do not necessarily have to be probability measures, and in fact, they could very well have different masses, then instead of looking at dynamical continuity equation, you look at dynamical ODEs, if you'd like. dt rho equals rho times r, where the reaction rate r is the control parameter that you will tweak to adjust your dynamics in the optimal way. And what you measure is somehow also a kind of kinetic energy, but it's not mass rho times velocity v squared. It's just mass rho times reaction squared, r squared. And if you minimize this, what you recover is actually a distance, or a squared distance, the squared of the Fischerial distance on the space of measures. And this is very well known and popular actually in statistics because it's very much related to the Fisher information metrics in information theory. So I do not have time to elaborate on this, but this is a well-known distance. And the fundamental example that I also want to cover here is the very same example. So you take two Dirac deltas, again, ρ0 at point x0 and ρ1 at position x1. And it turns out that the minimizer in the definition of this Fischerial distance is very different from the previous optimal transport. It's not a Dirac delta mass that travels horizontally at point xt. is just mass stays put, sorry, at the same position. So it's not horizontal displacement, but the mass of x0 will decrease in time and the mass of x1 will increase in time. And actually, you can even compute the explicit solution. So it's essentially linear interpolation between the square roots. So the optimizer rho t in this particular example is just you take square root of rho 0, 1 minus t square root rho 0 plus t square root rho 1. So you see this is the usual linear interpolation between the square roots, and then you take the square of that. So this allows for mass variations, right? So here you notice that since I did not put 0 in any right-hand side whatsoever, I can cover actually the case where the mass of rho 0 does not match the mass of rho 1. And this is rather based on the vertical displacements. Now, what you can do is combine these two different types of behaviors. So horizontal displacement, Wasserstein optimal transport, and vertical displacement, reaction Fischerial. You can combine this into a single framework, which is actually recent, which is called unbalanced optimal transport. So the definition is as follows. You take two positive measures, rho 0, rho 1, again, could have different masses, and fix a parameter kappa. So now what you look at is continuity equations, dt rho equals divergence of rho v plus rho r, where now you have two control parameters. You can choose v for the horizontal displacements of particles, and you can choose the reaction rate r to create or destroy mass. And what you infimize is the sum of the two previous costs. So you recognize here the squared kinetic energy, and here the squared reaction energy weighted by this parameter kappa squared. And you need a parameter kappa because you might want to weight differently the importance of these two phenomena, right? So when you infimize over all such pairs, the theorem is actually that this infimum defines the square of a distance, which is called the Wasserstein-Fischer-Rao for the obvious reasons. And you can think of this as an infimal convolution between horizontal optimal transport and vertical reaction Fischer-Rao in some sense. So this, just for the references, this has been discovered by three independent teams. The first one is Kondratiev, myself, and Vorotnikov. So I call this the Portuguese team. The second one is the German team, so Liero, Milko, and Savare. This is actually a paper in Invenciones. And the third one is a team from Paris, which is Shiza, Perret, Schwitzer, and Vialard. And although the dates here differ by quite a lot, so 2 years, actually all three preprints came out like within 3 months. So it was just, one of these times where everything happens at the same time. Okay, so let me just, for the record, talk for a little while about convex analysis. It's just about convections. So here is the previous Lagrangian action that I was minimizing to define the Wasserstein-Fischer-Rao distance. So again, squared velocity here, squared reaction, and everything is weighted by rho. What you need to do to define a proper minimization problem over measures, which is needed to make sense of this in the most possible general scenario, is to use, instead of the rho v r variables, so the primal variables, if you want, you need to change to the so-called mass momentum variables. So instead of using rho v and r, you use here rho v, rho r. So again, if rho is a mass, v is a velocity, rho v is what physicists call momentum. So I personally think of this rho v as a horizontal momentum and rho r as a vertical momentum. And if you want to express the previous Lagrangian here, this is becoming a mess, the previous Lagrangian v squared plus r squared times rho in terms of these new variables rho, g, and f, then this is the expression you get. And it turns out that this function, as a function of rho, capital G, and little f, is one homogeneous and convex. And this is exactly what you need to extend the definition of an integral functional to the space of measures instead of functions of x, if you like. So now the constraints, the continuity equation, dt rho, here this one becomes dt rho plus divergence G equals f, and you get this new Lagrangian in terms of the new mass momentum variables. So this is just for convenience. Okay, and now let me get to the core of the matter. So what I want to do is construct a model that lets the bulk and the interface talk to each other. So here is a map of a randomly chosen city, right? And oftentimes in city, you have So I had to look up the word. In English, it's called a ring road. So you have a fast lane that goes around the city so as to facilitate, the flow of cars. And essentially what I want to think of is this ring roads. I'm just going to say road for simplicity. So the roads is the surrounding boundary of your interior domain. And then you want to keep track of the cars on the ring roads inside the city, but they're allowed to move from the road to the city and vice versa. So this is what I want to do, right? So I want to build a model based on optimal transport and on this idea that there's a bulk and an interface that talk to each other. And the way to do that more rigorously is as follows. So here I have my domain omega. Let me recall once again that omega is compact. So the boundary of omega is included in omega, actually. And let me call capital gamma the boundary itself. So now I want to distinguish two types of cars. I want to distinguish blue cars that live inside the city and red cars that live on the ring road. Okay, so these I'm going to denote by little omega and little gamma. Okay, blue and red here. However, let me stress one last time that here you see the omega measure might have a contribution on the boundary. And if you think of it as a car, it means that on the roads, there can be two types of cars. There's the blue types of cars and the red types of cars, okay? So my primary space is going to be the space of pairs omega gamma, which are both positive measures. Omega v lives on omega, little omega lives on capital omega, and little gamma lives on capital gamma. And the requirement is that the total quantity of cars remains constant. So the sum of the two masses of those two measures should be 1 always. And this is what I denote by this calligraphic P plus of omega. The plus stands for sum has to be 1. So in the rest of the talk, I'm just going to say probability measures, but when you hear probability measure, you should think pair omega gamma such that the sum of them is a probability measure, okay? And the key ingredients I want to put in the model is that particles are allowed to drive in the city, they're allowed to drive on the roads, and there's a toll to pay. So if your road is actually a highway, you know that to enter the highway, well, actually not in Germany, so I've heard, but at least in Portugal, if you want to enter the highway, you have to pay a toll. And this is going to be described by a parameter kappa in my model, okay? So you pay to enter the road, but you also have to pay to exit the road. I have to make the model somehow symmetric. So the rigorous mathematical definition is as follows. So now pick two measures, rho 0, rho 1. One last time, rho 0 and 1 are actually pairs omega 0, gamma 0, and omega 1, gamma 1. One inside the city, the other is on the road. And what you do is you allow for a dynamical evolution of those two pairs of measures, as omega is only allowed horizontal transport inside the city. Gamma is allowed to transport along the road. So this divergence here is an intrinsic Riemannian divergence on the road only. So if you like, it's a tangential divergence. But there's also a reaction term, little f, on the continuity equation for gamma, if you like. And the condition I put that will be required to ensure mass conservation is that the outflux of the momentum in the city must match the influx little f on the road. So in different words, if I'm a blue car, I'm driving, I end up at the toll gate, I pay the toll, then I do not disappear. I just become a red car. That's it. I change color, if you like, right? And this can happen in a dynamical way. And the way to penalize, to compute actually the Lagrangian, how much energy this requires is, you should recognize here. So this is the pure Benamou-Brenier action functional. So this is actually V squared times omega, if you think of capital F as V times omega. And this is the unbalanced optimal transport setting that I showed you previously. So you mix together these two ingredients. But the main point is really that the coupling is through the flux condition. The outflux of the city cars must match the reaction rate, so the influx, if you like, of cars on the road. One important observation is that by construction, there's conservation of total mass. because I just told you, you don't just disappear. If you enter the road, you just become a red car and you don't disappear out of nowhere. So the total mass, calligraphic rho, which is the sum of those two measures, is actually a probability measure on the whole space, on omega bar, including the boundary, for all times. So the coupling only occurs through this kind of flux condition, but it's actually quite tricky. If you write down carefully the weak formulations of these two continuity equations, you realize that little f can be non-zero, although capital F is zero, which might seem weird, right? Because if you write here that the outflux of capital F must be little f, it seems weird that little f is non-zero, although capital F is zero. And this is because essentially I'm allowing blue cars to be already on the road somehow. They just have not paid the toll yet, but blue cars can charge the boundary of omega themselves. Okay, so let me give you a typical proof, or actually sketch of proof, which is a very good example of how these three processes mix together. So horizontal transport in the city, horizontal transport on the roads, and vertical transport, vertical reaction on the road. So let me prove, for example, that this quantity that I defined is always finite, right? So here is again the dynamical, the kinematics that I'm allowed to use to move around mass. So the situation could be as follows. So I have blue cars somewhere spread inside the city, possibly also here on the road, okay? And I have red cars that are already on the road. So what I can do is pick any point x star on the boundary here. Then as a first step, what I can do is use pure mass conservative optimal transport in the city only. So the red cars are not moving, they're not going anywhere. I use a pure Wasserstein transport to bring all these blue guys all to the direct delta mass located at x star. And this I'm allowed to do because omega is closed compact. So the blue measure is allowed to charge the boundary, okay? And this has a finite cost because this is well-known classical optimal transport. So here's the situation now. The blue mass I've brought back all to the same point x star. Now you can see what's coming. Probably I can do exactly the same using pure optimal transport along the road only. And this is the picture. So no reaction yet. There's no interaction between the two species whatsoever. Now the blue mass stays put, doesn't do anything. It remains at x star, and only the red cars drive along the road to all end up at position x star. And this I can again do by classical optimal transport on the boundary. This has a finite cost. So here's the situation. I have all my blue cars and all my red cars concentrated at the same single point x star. And then as the last step, what I'm going to do is use the pure reaction, so the Fischerial pure reaction, to transform blue cars into red cars, which I'm allowed to do also here. And this again has a finite cost because it's precisely the definition of the Fischerial distance. And this is what you end up with. So all the blue cars have been transformed into red cars. You only have red cars at x star. All the blue cars have somehow disappeared. Well, they didn't go away. They just, turned into red cars, but that's what happens. And as a conclusion, what I just did is I started from an arbitrary rho zero and I connected it for a finite cost to the probability measure rho star, which is 0 in the city and 1 at x star for the red cars. So by symmetry, if I can connect any rho 0 to this rho star, I can connect rho star to rho 1 and therefore rho 0 to rho 1 with a finite cost. And this is all I need, okay? So you see that here, these three processes, horizontal transport in the city, horizontal transport on the road, and vertical reaction kind of play together nicely somehow. It's very flexible, okay? So one thing I want to address is duality. So first of all, why should you look into duality? Well, the good reason is that oftentimes when you have an optimization problem, if you look at the dual problem, you gain some insights. You learn a lot actually about the structure of optimizers. So how do you do that? Symbolically or informally, if you like, here. So say you have an infimization problem with constraints that X should belong to some constraint space C. The first thing you want to do is rewrite the constraints that X should belong to C by using a Lagrange multiplier lambda. So the role of lambda is to encode that X is constrained, but now the infimization over x becomes unconstrained because you use the multiplier lambda to encode the constraint. And then, under reasonable convexity or concavity assumption, usually you can use convex analysis to swap inf sup equals sup inf. And this is how you write the dual problem. This is a very general trick. This is how one usually gets the dual problem. So if you do so here, what happens is that you can prove the following duality results, that the squared distance, the ring road distance, can be written as a supremum over smooth functions psi and phi. So psi and phi here, or if you like, my Lagrange multipliers, psi phi or the lambda in this abstract notation here. So the supremum of integral of phi1 omega 1 minus phi0 omega 0, so phi1 and phi0 are just phi evaluated at time 1 and 0, minus psi1 gamma 1 minus psi0 gamma 0, such that phi and psi are subsolutions of the following Hamilton-Jacobi system. It doesn't really matter the precise form of the system. So this comes as no surprise for people in optimal transport. However, there's a non-standard coupling between the phi and psi species. So phi is a multiplier for omega, so the city cars, and psi is a multiplier for the road cars. But there must be coupled, of course, because city and road cars are coupled to each other through the flux. So phi and psi must be coupled, and you see that the coupling here occurs through this term. Okay. And let me give you one example of why it's so powerful to look into duality. So this is the dual problem. Once you have this duality result, it's very easy to prove the following thing, that if you fix two measures, ρ0 and ρ1, the distance as a function of kappa, so kappa is my toll parameter, right? The larger kappa is, the more expensive it is to get on the road. Then this is a monotone increasing map as a function of kappa. And the proof is actually not so trivial if you look at the primal problem. Now, if you look at the dual problem, it's actually a one-line proof. It's enough to notice that here, this function as a function of kappa is non-increasing, which means that for fixed phi and psi, if you are a subsolution for a small value of kappa, you're automatically a subsolution for the large value of kappa, which means that the set of subsolutions is increasing for the inclusion with respect to kappa. And when you take the supremum over larger sets, you increase the value of the supremum. That's it, right? So that's the first insight you get by looking at the dual problem. A second insight you get by looking at the dual problem is the following. So I just rewrote here the dual formulation of my distance. So I have a sup of this quantity such that phi psi are subsolutions. But now think for a second that omega 0 is fixed. Phi 0 is fixed. Just let's assume it's fixed for some reason. Now, if you want to compute this sup, you'd better make this phi 1 as large as possible, right? In order to increase the value of the supremum. However, if phi is a subsolution, the only thing you can do is that the largest possible value of phi at time 1 is when phi is actually a solution of the Hamilton-Jacobi equation. And this is just because Hamilton-Jacobi problems enjoy monotonicity properties. So Hopf-Flachs monotonicity properties, if you want. And this suggests the following, that if you want to look at optimizers, so solutions of the minimizing problem, of the minimization problem, or actually maximizers of the dual problem, you should saturate inequalities in the Hamilton-Jacobi subsolutions. And what you can prove rigorously is the following certification theorem. So it's a sufficient optimality condition. So if you can find a pair omega gamma that solve the continuity equation here with, what I call potential kinematics, means that the velocity field in the road is gradient of phi, the velocity on the roads is gradient of psi, and the reaction actually involves both phi and psi. So if you can find a solution of the continuity equations such that this is true and phi psi are actually solutions of the Hamilton-Jacobi equations and not just subsolutions, then automatically you know that you get to geodesic. You get an optimizer in both the primal infimization or dual maximization problem. So what this allows you to do is, it's actually a very convenient tool because it allows you to actually check optimality. So if you think you have a good candidate for a minimizer, then it's enough to check this sufficient condition. And it's almost necessary, actually. So let me illustrate this on a fundamental problem, which is the following. So in classical optimal transport, so mass conservative optimal transport, where you don't distinguish blue, red cars, you only have one type of cars. So Wasserstein optimal transport, if you like. A fundamental feature of optimal transport is the so-called Eulerian-Lagrangian duality. One way to say that is that if you compute the Wasserstein distance between two Dirac deltas, one located at x and the other located at y, this is exactly the squared distance in the omega domain between position x and y. Okay? And this has a lot of consequences in the theory of optimal transport. I don't want to go too much into the details, but this is very crucial in optimal transport. Therefore, it's a very natural question to ask here, can we do the same for my bulk interface problem? So here's the picture. You have again your CD omega, you have a road gamma, and what you want to compute is the geodesic between two types of Dirac deltas, one which starts in the interior. So omega is just a Dirac mass at x0, and there cannot be, there's no delta, there's no gamma. So there's no red cars here. This is your zero measure, and the measure at time one should match actually the other way around. So there's no city cars, and there's only roads cars located at position XR on the boundary. So what you want to do is compute the geodesic and the distance between those two measures. So first of all, clearly, it's a one-dimensional problem, so everything will take place along this one-dimensional segment, capital I, that joins the 2 points in my domain, okay? The second thing is that contrarily to optimal transport, where you would have just, the traveling Dirac delta that I showed you actually, I think in the second slide, the horizontal Dirac delta that travels from x0 to x1, this cannot happen here. Because if that was optimal, you would have no mass on the roads, no mass for time 0, no mass at time 1/2, no mass at time 3, 4, and so on, until the very last time, at time t equals 1 minus something very small, where suddenly the mass of cars on the city jumps from 0 for all previous times to 1, because you need to match here the constraints that your terminal marginal is given by you have 1 unit of car on the road at time 1. So, and this is not compatible with the flux penalization that I built in my model, right? You cannot jump that because it's essentially an L2 in time integral. So this will have infinite costs. And also, it cannot be a concatenation of two simple processes. So you might think, okay, first maybe in time 0, 1/2, I'm going to transport my Dirac delta from x0 to xr, then stop transport, and for the remaining time 1/2, 1, use pure reaction to transform my blue car into a red car. But this is not optimal as well. This does not satisfy the previous system of Hamilton-Jacobi equations because it creates shocks. So it means that it must be more complicated. So here's the answer. So again, I'm just drawing a one-dimensional picture. I told you everything takes place on the one-dimensional segment, capital I here. So I have 1 unit of red cars in the city, so at r equals 0, and 1 unit of blue cars at r equals capital R here. So here is an explicit formula. You compute this exponent alpha. I will comment on the numerology later on, but you compute this exponent, which is always larger than 2, and then the distance is given by this explicit formula. Okay? But more interesting is actually the expression for the geodesic. So let me comment on this. Omega t is what? So you see here there's an indicator function that moves in time. So the left-hand point of the indicator is a point that will move from 0 to r linearly in time. And as far as the spatial profile is concerned, for a fixed time t, you have essentially here 1 over r to the power alpha plus 1. So some negative power of r. So let me draw a picture instead of words. This is what it looks like. So this is the initial configuration. So you start with 1 unit of red cars on the left, and then this is what happens. So let me rewind. At time t, you see here that the red measure omega t is located only in the interval RTR. So this is what this indicator does. And then as far as the spatial profile is concerned, you have some kind of decreasing algebraic power profile of the radial coordinates, okay? And the blue mass grows algebraically in time. So gamma t is some power of t, okay? So you see here that actually particles, the red particles kind of travel inside the domain with velocity here given by this, this vector field. They move, they move, they move. Here, cars somehow arrive at the boundary, they pay the toll continuously, and they contribute to growing the number of blue cars, right? So you see here that this blue density is monotone increasing in time because there's more red cars pushing and they keep arriving and paying the toll and passing the toll and so on. So this is what happens. And there's a striking difference with the optimal transport, which is this is the profile of the density in the city, the red profile here, at time, say, t equals 1 to the minus 6. And what you notice is that instantaneously, there's cars everywhere in the city. Well, not here, but cars, they all start at 0, but as soon as t is strictly positive, cars have already arrived at the toll gates, right? Which means that, contrarily to optimal transport, particles actually travel with unbounded speeds. So pay attention. I'm not saying that some particles travel with infinite speeds. I'm saying that there's many particles, and you cannot give an upper bound on the speed of such particles. So every particle that you look at has a finite speed, but the value of the finite speed can be arbitrarily large, okay? This does not happen in optimal transport, in classical optimal transport, because in classical optimal transport, the furthest that a particle can travel is essentially the diameter of your space, right? So if omega is no larger than 2 in diameter, then particles will travel in time 1 over a distance at most 2. So the speed is going to be bounded by the diameter of your space divided by 1, because all particles travel over a time 1. So this means that this model of optimal transport is very different from classical optimal transport. So let me maybe skip the numerology because I need to move on, but let me give a quick idea of proof. So actually, in order to make everything rigorous, I can use the previous certification theorem. I gave you a theorem saying that if you find a pair of solutions to the continuity equation such that blah, 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 then necessarily you're an optimizer. It's a sufficient condition. Then all I have to do now is find a clever ansatz and check a posteriori that my ansatz does satisfy my optimality conditions. And this is exactly what I'm going to do. So, however, it's actually different from optimal transport. So here is the ansatz. The ansatz is you want to view your continuous measure omega t as a continuum of infinitesimal Lagrangian particles, capital X, T, Y. So Y is a label that I'm using to keep track of all the different red cars, right? So maybe this particle has label Y, this particle here has label Y1, there's another particle with label Y2, and so on. So I have a whole continuum of particles that move around. And the main difference with optimal transport is that if I look at a fixed time t, well, particles drive towards the toll gates, but once they reach the toll gates, they kind of disappear from the city. They become blue cars. So I don't need to keep track of them anymore as red cars, okay? So this means that even though I start with labels y in 0 and 1, at time t, I only need to care about labels y in between 0 and some label capital T, capital YT, and the set of labels 0 capital YT is the set of labels that are still within my city at time t. The other cars that have already entered the road, I forget about. I just ignore them from now on. Okay? So this formula here is just the Eulerian superposition, saying that my continuous measure omega t as I choose to view as a continuum superposition of such Lagrangian particles. So each particle xt gives rise an infinitesimal Dirac delta at position capital XTY with infinitesimal very small mass dy. Okay, and the trick is guided by a classical optimal transport. I choose that all my particles should have constant speed. So constant speed does not mean that all particles have the same speed. It means that if I look at one particle with label y, it will keep the same velocity over time. Two particles with different labels can have different speeds. But once I choose to look at one particle with label y, it will have a constant in time speed, which is what I write here, u of y. And if for some reason you choose what u of y is, then you can determine everything. Because if you know the velocity of each particle, you know exactly how much time it will take to start from 0 to reach the boundary. Essentially, it would take distance divided by speed. So if you know the speed, the distance is r by definition. So if you know the speed, you know how long it takes to reach the boundary. You can determine everything. You can determine the influx here of omega that will actually contribute to growing gamma, and so on. And what you want to do is optimize the resulting cost. So the cost is here a purely kinetic cost. So you see here that this kinetic cost is what? So dy is the infinitesimal mass of my particle. U squared is the velocity of this particle. So dy times u squared is the infinitesimal kinetic energy of the y particle. Now, this particle reaches the boundary not at time 1, as it would do in classical optimal transport. It reaches the boundary at some time tau that depends on y, which is explicitly determined by the velocity u, right? But this you can compute explicitly as a function of u. And there's also a reaction part that I'm not going to bother writing, but that you can also compute completely explicitly as a functional of u, right? And then you just minimize this. It's a simple exercise in the calculus of variations. You minimize this with respect to the function u of y, and this allows you to guess what the ansatz is. Then you can reconstruct everything. So you can reconstruct omega, the velocity fields, the reaction rate. You can reconstruct all the variables, and you check that the ansatz you get is actually optimal, right? So what about the nice properties of this distance? So let me write, which I did already, rho calligraphic, the sum of the city plus the road cars, right? So calligraphic rho is what? Is just forget about the colors, right? I just look at how many cars I have around, regardless of whether they're blue cars in the city or red cars on the road. I do not distinguish anymore between the two types of cars. So what you can show is that you can sandwich this ring road distance in between. On the left-hand side, the classical optimal transport between these calligraphic rows, so where you kind of don't discriminate between cars or colors. And on the right-hand side, the Wasserstand distance between the city cars plus the Wasserstand distance between the road cars, okay? And let me remind you also that this quantity in the middle, so the ring road distance, is increasing in kappa, okay? Both these inequalities are actually sharp and can be strict. So you cannot get better than this, right? I can cook up counterexamples of rho 0, rho 1, where either of these inequalities are strict, and I can cook up examples where the inequalities are actually equalities. So that's the best you can say in a whole generality. However, well, first of all, maybe some additional properties of this distance. What you can prove is that the metric space is complete, which is a very desirable property if you want to do analysis on metric spaces, for example. For this whole machinery of gradient flows in metric space and blah, 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 you need completeness. So hopefully, I mean, so far so good, we do have completeness. And moreover, the topology induced by this distance is actually very natural. My primary variable are not just probability measures, they are pairs, omega, gamma. And I choose, by very construction, my model discriminates between blue omegas and red gammas, right? So the topology that is induced by this metric has the good taste of metrizing two separate weak convergence of measures. So by weak convergence of measures, I mean duality with the continuous and bounded test functions. This is a very common and a very weak topology. So my metric metrizes exactly this double narrow convergence, right? So rho n converges in distance to rho if and only if omega n converges to omega and gamma n converges to gamma, which is again very desirable. It's nice to have that. But going back to this inequality is one, once I have sandwiched my distance in between those two quantities and knowing that the bounds are sharp and that the middle quantity is increasing in kappa, it seems very natural to ask what happens when kappa goes to 0 or plus infinity, which are the two external values for this value of the toll parameter, right? So this is the theorem. When kappa goes to 0, so you fix rho 0 and rho 1. Everything is pointwise. So you fix two measures, and you look at the limits of the large toll, kappa going to plus infinity, or the small toll, kappa going to 0. So the first result is that when you send kappa to 0 here, the ring road distance converges to the Wasserstein distance in the whole domain between the total densities of cars. So this calligraphic rows, which is just the sum, again, omega plus gamma. And this is very natural. This should be expected. Why? Because when kappa goes to 0, what happens is that the cost that red cars need to pay to enter the road becomes negligible. It's almost, and actually in the limit, you can enter the road for free. And if you can enter the road for free or actually get out of the road and come back to the city for free, there's no more reason to distinguish between red cars and blue cars. The only thing that matters is how much cars you have around, right? You don't need two different colors to label two different types of cars. And this is exactly what this result says. The second part of the result says that if you send the toll to infinity, kappa to plus infinity, the ring road distance converges to the sum of two square distances. One is here the Wasserstein distance between the city cars plus the road cars. And pay attention that actually both of these quantities can be plus infinity if, for some reason, the mass of omega 0 is not equal to the mass of omega 1, or equivalently, if the mass of gamma 0 is not equal to the mass of gamma 1. And this is, again, also extremely natural, because when you send kappa to plus infinity, it means that it becomes infinitely expensive to jump from the city to the road, or vice versa. And therefore, in the limits, no transfer of mass can occur from one to another. So you kind of uncouple completely the city and the road. Whatever was on the road to start with remains on the road forever. So the only thing you can do is drive on the road in an optimal way, sure, but you cannot, bring in new cars or send out cars back from the road to the city. This cannot happen anymore because it's infinitely expensive. Okay. So this means that in some sense, my ring road distance interpolates monotonically between these two optimal transport problems. One is the classical optimal transport problem between the total cars, the total density of cars, where you forget about colors. And the second one is two uncoupled problems. One is optimal transport inside the city, and the second independent optimal transport is optimal transport on the road, which is, I think, a very nice property of the model, which is exactly what I had in mind when I started doing this whole thing. Okay, so I think I'll just finish with a few perspectives because my time is, my time is done. So the first thing I want to do, of course, is look at static formulations. And Jan mentioned this already, and I think this is fascinating. I personally believe that there cannot be any static formulation, but this is for another day. The second thing I want to look at now is gradient flows. So identifying coupled systems of PDEs, bulk interface couplings included, as gradient flows with respect to these coupled metrics. And in particular, what I would be very much interested in is consider models where you actually have interfaces. So instead of having a fixed road which does not move at all, it would be kind of, you allow interfaces to move dynamically according to this type of phenomena. So far my model does not cover this, but this is one direction which I think is very natural, actually. Another possible lead of research is considering more complex structures. So instead of considering bulk interface interactions between the boundary of the domain, you could imagine that you have lower dimensional tracks. So you have a 3D domain, but you have a one-dimensional track within your domain. That's possible. And possibly also different mobilities or different ways of penalizing the flux costs. And finally, one thing I want to mention is that in the paper by Martin, Ina, and Jan, they considered essentially this almost the same type of model, but instead of considering on the Euclidean domains where the interior of the domain is coupled to the boundary, they look at it on one-dimensional graphs, or actually, sorry, two-dimensional graphs with the one-dimensional edges connecting zero-dimensional vertices. However, what they penalize as a flux, so now mass can actually move around the edges, and then they can kind of enter from an edge to a vertex, or vice versa. Get out of one vertex and jump back in on one of the edges. But the flux penalization they put was if you're at an edge I here, you look, what they did is this. So the way to penalize the flux is you look at the effective overall costs. So this is, if you're sitting at edge, at vertex I, you look at all the influxes from all the adjacent edges. So each time you do that, you have a flux Fij, which is an influx from the jth edge to the ith vertex. You sum all of these. This gives you the effective net flux at the vertex I, and then you square this. And actually, with respect to my model, a more natural thing to do would be, instead of taking the square of the sum, taking the sum of the squares, which is very different, actually. As we briefly discussed with Jan, I think there might be a very different perspective here. Actually, I think both models are interesting for possibly different models that one has in mind. So I don't know what's going to happen, but here is just a picture again. So 0 here is one vertex, and you have two adjacent intervals that connect through this common vertex 0. So say you want to connect a Dirac delta mass in the interval I1 to a Dirac delta mass on the interval I2. If you choose to penalize your flux according to this law, what the geodesic should look like is something like this. So you start at time 0, you mass slowly reaches the vertex, the mass jumps in from the I1 interval here to the 0 vertex, and this is what this influx little f1 does. Meanwhile, you also have an outleak of mass from this kind of vertex to the second interval, and so on. So let me just run the picture. This is what it should do, I guess. But this is still unclear, and my time is way over, so please forgive me, and I think I'll stop here. Thank you.